So our next speaker is Kiseok Yeon, who will talk about cubic diagonal hypersurfaces. Please.
Okay, thank you for introduction and thank you for giving an opportunity to present the result. Actually, while listening to the talks this week, I found that some people mentioned the use of AI in the proof. That sounds very exciting and interesting, but very unfortunately, this talk is about completely human-based proof. Okay, today I'm going to talk about on the density of rational lines on diagonal cubic hypersurfaces. This is joint work with Scott Parcel. Give me a second. Okay, so I begin with a brief history and motivation. The problem of establishing the existence of linear spaces on algebraic varieties was initially studied by Brouwer and Birch. In particular, Birch's work here proved that if you are given algebraic varieties of sufficiently large dimension, and if this variety is defined by a system of homogeneous polynomial equations of odd degrees, uh, then this variety contains linear spaces of desired dimension. But because of the inductive nature of their argument, they didn't specify how much large the dimension should be to contain linear spaces. So the natural question would be, how large must the dimension of an algebraic variety be to contain linear spaces? So I note that the smaller dimension you require, the better result you get when you answer this question. And so once you have a sufficiently large dimension, then next question may be how many linear spaces lie on the variety. So I'm going to call these quantitative questions. In this direction, progress has been made by Uli and Brands after the work of Brouwer and Birch. In particular, the case in which the algebraic variety is defined by a system of cubic forms has received significant attention, beginning the work of Lewis and Schurze-Pilote in 1984. And further refinement have been made by Uli, Brands, Dietmann, Lipp. Okay. Another case that has received attention is the case of diagonal hypersurfaces. Consider the hypersurface defined by a single diagonal form of degree k in S variables with non-zero integers coefficients. And then you can ask the same question on linear spaces on this hypersurface. And also you can ask the quantitative questions we described before. Beginning the work of Arikov, Karatsuba, Chubarikov, the quantitative progress has been made by Parcel, Prendiville, Uli. Our main interest is lines on diagonal cubic hypersurfaces. Basically, we are going to restrict linear spaces to be lines and algebraic variety to be diagonal cubic hypersurfaces. And first, we are going to set up the quantitative question in a more rigorous way for lines on diagonal cubic hypersurfaces. Okay, consider pairs of integer vectors x and y such that the line L written by x plus ty is contained in the hypersurface defined by diagonal cubic form. So to include the line x plus ty in the diagonal cubic hypersurface completely, if you substitute the expression x plus ty into z in the equation, that equation must hold for all parameters t. That means the coefficient of part of t should be vanished. So by using binomial expansion, you get vanishing coefficient to provide the system of equations labeled by 1 below. And also note that the counting the lines L expressed by x plus 2y lying on the diagonal cubic hypersurface is same as counting integer pairs x and y, satisfying the system of equations 1. So we are going to call this system our target system because it's the most interesting system of equations to us. And define a quantity ns of x to be the number of integer pairs x and y running over 1 through x, satisfying our target system of equations. And here is the result. Okay, whenever s is greater or equal to 18, we have the expected asymptotic formula for ns of x. That is sigma times x to the 2s minus 12 plus error term. And the coefficient sigma is a positive constant depending on coefficients c that appear in our target system of equations. Under the square root cancellation heuristic, this bound should be improved to s is greater or equal to 13. So 5 variables left to attain this conjectured bound. Previously, the work of Zhao in 2016 proved that obtained the same asymptotic formula for s is greater or equal to 21. And prior to this, the Parcel obtained the bound s is greater or equal to 29. So I'm gonna provide a sketch of proof of this work. Before doing that, I'm gonna provide an overview of the new idea we used in the paper. The standard approach is to relate our target system of equations to a structured system of equations, so-called Parcel-Vinogradov system. And by applying the sharp estimates for Parcel-Vinogradov system due to Bulgang, Dimitar, and Guo in 2017, you can deduce that whenever s is greater or equal to 21, you have the expected asymptotic formula. You notice here that this bound is the same as that obtained by Zhao in 2016. When Zhao announced the result, we didn't have the sharp estimates for Parcel-Vinogradov system. But thanks to these sharp estimates, due to Bulgang, Dimitar, Guo, we can recover the result of Zhao in a quite straightforward way. And our approach is a bit different. We are not going to relate this target system to Parcel-Vinogradov system directly. When you relate that to Parcel-Vinogradov system directly, a huge loss occurs. So just by relating the target system to a less structured system of equations, you could avoid that huge loss. And also, we are going to approximate this less structured system of equations to Parcel-Vinogradov system through another argument, so-called shifting variables argument. Then you can deduce that whenever s is greater or equal to 18, you have the expected asymptotic formula. Okay, but this is not the first application of shifting variables argument. That is actually initially developed by Oli in 2012, where he improved the least required number of variables to have the expected asymptotic formula in Waring's problem. That result is still world record up to the date. So, okay, I begin with the setup for the circle method. To talk about the sketch of the proof of the main result. So recall that our main quantity ns of x is the number of integer pairs x and y satisfying the target system of equations. And if you define the exponential sum FC of alpha as following, then you find that by orthogonality, this quantity can be seen as the mean value of exponential sums. So to deduce the asymptotic formula for the quantity ns of x, it is enough to study the mean value of exponential sums in the right-hand side, labeled by 4. So to do so, we must define major and minor arc. So major arc is nothing but a collection of real vectors in the unique cube of dimension 4, having a good rational approximation with common and small denominator. And the minor arc is simply the complement set of major arc in this unique cube. So using this major and minor arc dissections, we could split the mean value of exponential sum into two parts: mean value over major arc, mean value over minor arc. It is already known that mean value of a major arc provides the main term, sigma times x to the 2s minus 12, whenever s is greater or equal to 16. So that is smaller than 18. So it is enough to study the mean value of a minor arc and prove that this mean value of minor arc gives the error term, big O of x to the 2s minus 12 minus tau for some positive tau. Meanwhile, by the standard argument through the Haldane inequality, you can obtain the upper bound for the mean value of a minor arc in terms of the number of integer solutions satisfying the system of equations labeled by 5. This system of equations looks similar to our target system of equations, but it doesn't have coefficient Ci, right? So you can simply remove that coefficient Ci using the Haldane inequality. So our target system of equations has been changed to this, labeled by 5. So we are going to call this new target system of equations. So, okay, let's consider this new target system of equations. But this has lack of structures to obtain a satisfactory bound for the number of integer solutions, at least in the current state of knowledge. So we are going to rather consider this system 6, 7, 8 by adding additional system 7 and 8 with red color. So these are all looks similar, but if you look at the system 7 and 8, the system 7 is a system of quadratic forms, and the system 8 is a system of linear equations. This is precisely the Parseval-Vinogradov system, and it has a good structure. More precisely, if you have a integer solutions to this system 6, 7, 8, then any shifted pairs x minus z1 and y minus z2 becomes also solution to this system of equations. Moreover, by the work of Bulgang, Demeter, Guo, as I mentioned before, the number of integer pairs x and y satisfying Parseval-Vinogradov system is bounded above by x to the epsilon times x to the s plus x to the 2s minus 20. I emphasize that this is essentially optimal bound because you could obtain the lower bound for this by x to the s plus x to the 2s minus 20. So this upper bound is tight up to x to the epsilon loss. So at this point, one may be curious about how to link between our new target system of equations and this well-structured Parseval-Vinogradov system. Because originally, we want to count the number of integer solutions satisfying only 6, but we have been talking about a parcel of systems 6, 7, 8. So here is the procedure. Let me temporarily define the quantity JS x0HL to be the number of integer pairs x and y satisfying the system of equations. But this system of equations is different from parcel-Vinov system, because if you look at the right-hand side in the systems 10 and 11, you have constant hj and lj. Those parameters do not have to be zero. But if you set up h equals l equals 0, this system's turned into a parcel-Vinov system. So, um, so we find that the number of integer pairs satisfying only the system 9. Okay, system 9 is exactly the same as our new target system of equations. So the number of integer pairs satisfying the new target system of equations 9 is equal to summing over the parameters h and l of the number of integer solutions satisfying 9, 10, 11. This is because any integer solution satisfying only 9 has its own value, hj and lj, if you substitute that solution into the system 10 and 11. So if you sum over all the values h and l, then you can capture all the integer solutions satisfying only 9. Right? Any questions so far? Okay. And it is known by applying the triangle inequality, the number of integer solutions satisfying above system of equations is bounded above by the number of solutions of parcel-Vinov system. So if you use this trivial upper bound, the summation over h and l of js of x0hl is bounded above by summing over summation over h and l of the number of integer solutions of parcel-Vinov system. But the solution of parcel-Vinov system do not depend on the parameters h and l. So just by simply multiplying the cardinality of h and l, you get the bound x to the 8 times js x000. And here, if you apply the work of the Bolgang, Demeter, Guo in 2017, and then you get you get the bound x to the 8 plus epsilon times x to the s plus x to the 2s minus 20. So through this argument, you can recover the result of Zhao, as I mentioned before. Whenever s is greater or equal to 21, you have the expected asymptotic formula. But I'm not going to explain how to obtain this bound s is greater or equal to 21, because we have time constraint. This is but the key idea is the key procedure is just above, like the inequality is labeled by 12. So about the downside of this procedure is, if you look at the procedure 12 in the first or second step, we didn't take advantage of summing over h and l, because we only use the cardinality of the sets at h and l. So if I summarize it, what we have shown so far is to relate the system of our new target system of equations to the parcel-Vinov system. But as I mentioned, this approach does not take advantage of summations over h and l. So our new approach is to relate new target system of equations 13 to the system counted by JS x0h0 and taking advantage of summation over h. So if you remember, jx0h0 is, if you look at the system 9, 10, 11, if you set up L equals 0 and just leave h, that doesn't have to be 0. So we are going to consider these systems. So in order to take advantage of the summation over h, we are going to consider the following. So, but rather considering the system related to JS X0H0 directly, we are going to consider the shifted system. So that means if you substitute x comma y by x minus z1 and y minus z2, that gives the following new and long complicated system of equations. And if you use binary expansion, these systems can be seen as 14, 15, 16. So if you look at the right-hand side, in the system 14, you have multilinear function Lj of h z1 and z2. And if you look at the right-hand side in the system 15, it is still hj. If you express the number of integer solutions satisfying these systems, 14, 15, 16, in terms of the mean value of exponential sums, as we did through the orthogonality, then you realize that you have additional exponential sums over h, z1, and z2 due to the factor in the right-hand side in the system 14. And if you compare this mean value of exponential sums to that from the Parseval-Vinogradov system, yeah, so you have extra exponential sums because in the Parseval-Vinogradov system, all the right-hand side are all the right-hand side is equal to 0. So this additional exponential sum leads to an improvement to the bound s is greater or equal to 18 as desired. But we'll not talk about the detail how to obtain this bound because we have time constraint. But that is a very technical argument. Combine measure theoretic argument and interpolation. And also, my last word is if you naively follow the same argument in our work, then you could make progress on lines on diagonal hypersurface of higher degree, greater than 3, so beyond the cubic hypersurface. But that would provide just a small improvement over the previous result. So I think I should stop here. Okay, thank you
Okay.
for listening.
Thank you very much. Are there any questions for our speaker? If not, we thank Kiseok again, and our next talk will be in 6 or 7 minutes. So,
Thank you.
Florian, if you want to share your slides, then we'll be ready to start soon.
Oh, okay.
Oh, looks pretty good.
Maybe make it full screen.
Yep.
Is it full screen?
It is full screen and it's beautiful to look at.
Is it moving?
Yes.
Okay, cool.
So we will be in business shortly.
Okay.
So whenever I see you, Florian, you're somewhere not in South Africa.
I am usually in South Africa between maybe end of November to end of May.
Okay. So I guess I don't see you in that 6 month period or 7 month period.
That's true, yeah. So we have 2 semesters in South Africa. The first one starts around the beginning of February, and classes end around mid-May, and I'm teaching a course in that semester. And
Oh, that's
every
unusual
six
for you.
months, I'm in Europe for between June and November.
Okay. Um, but you seem to be a master of minimizing your teaching load.
Well, I'm getting a bit old. I used to have a teaching load of 0 for about 10 years. Now I'm teaching something. So
Ah, well, but it gives you a goal to aspire to in the future.
that's yes, yes, that's true. Yes.
So, has AI come to South Africa?
Well, it's there. I haven't actively used it yet, although every now and then I do ask Chat GPT certain things that I used to run a Mathematica code before. Now I'm becoming lazy. So instead of coding it, I ask Mathematica, can you reduce this polynomial for me? So I ask
Oh,
ChatGPT.
yeah.
But
I I I I should think of doing that, but I never do. But it really is.
well,
Yeah.
sometimes it gives the wrong answer. Sometimes you ask them something in one day and it tells you something, and you ask it the next day, it tells you something different. And then you say, but
I've
yesterday
asked
it told me this.
ChatGPT some math questions, and it will give an answer, but then it would say, "But I'm not sure this is correct." Uh,
I see.
I
Okay.
thought that was actually quite sophisticated.
So there's a disclaimer there.
Hmm. Well,
So how many participants were there at the conference in person? 50, 100?
no, 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 no. Um, so I can count the number of people in the room at any time, but I cannot count the total number of people who were there at different times.
I see.
So we might have typically, let's say, 25 to 40 or so people in the room, and maybe 30 or 40 or more people on Zoom. But uh, you know, if you get grants for your conference, then you have to write a report and you want to say how successful it was and how many people participated. Uh,
Mhm.
but I don't apply for grants and I don't have grants and I have no one I have to justify anything to. So someone the other day asked me how many people were registered. And I said I could go somewhere and try and look it up and count it, but life is short. And since I don't need to know, I don't know. Uh,
Okay, you just counted the talks, but of course there were more
well,
people than
the
talks. So.
talks, yeah, I have 80 talks, so I have to put them together. But you know, what I find nice is that for every talk, there are always people. And even
Mhm.
today, when I had to start at the ridiculous time of 7:30 in the morning, um, and I have to run this whole thing myself, so I literally listened to every minute of every talk. So we had 10 talks this morning, and we
I
have
see.
8 talks this afternoon. But even around 7:30 in the morning, I had 20 or so people who were online. Of course, when it's 7:30 in New York, it's the early afternoon in Europe and the
True.
evening maybe in Asia. So, but anyway, it's fine. Enough said. Let me start to record. And oh, damn.